Well, just say it verbally. What does it involve? There are 4 quantities. And so how do I get equations for these 4 quantities? Well, how many initial conditions are there, initial values? There's one for x1 and one for x2, so 2. How many eigenvectors are there? 2. What's important about the eigenvector? Is its size important? No, only its direction. So there are 2 initial values and 2 directions. These 2 initial values and 2 directions are what allow you to calculate what these 4 constants are. The theory is there in the textbook and in the notes. So the point I'm trying to make is that in order to understand what's going on, you have to first look at the eigenvalues. Now, if both eigenvalues are negative, what happens to these terms as t increases? They go to 0. So if both eigenvalues are negative, then z1 and z2 go to 0. What happens if one eigenvalue is positive and one eigenvalue is negative? What happens to the solutions? Let's say lambda 2 is negative and lambda 1 is positive. What happens to this term? If lambda 2 is negative, what will happen to the term as t increases? This will go to 0, and this will grow. So these 2 will grow, and they'll grow as controlled by this eigenvalue, with the directions initially, like the ratio of z1 to z2 will be the ratio of alpha to gamma. And that's where the direction will come in which it increases. If both of these are positive, then both of these will grow. So if both are negative, we're going to get a stable node. If one's negative and one's positive, then the one that's negative is going to go to 0, and the one that's positive is going to grow. But depending where you initially start out, it could look like it's decreasing first and then increasing. So that's where you would get the unstable saddle point. And if both are positive, then both are just going to grow in any direction. So the eigenvalues are going to tell you whether you've got a stable or unstable node or an unstable saddle point. However, there's still something called the spirals. Now, the spirals, what happens is that if these are not real numbers, how can these not be real numbers? What might happen? If I solve the equation, the determinant of a minus lambda I equals 0, that's the determinant of the matrix a minus lambda b c d minus lambda, which is equal to a minus lambda times d minus lambda minus bc. What is that? It's a quadratic equation in lambda. So when I solve this equation, I can get 2 positive solutions, 1 positive, 1 negative, 2 negative, but I can also get what else? What happens sometimes if you try to solve a quadratic equation? Okay, unfortunately I've used A, B, and C there, but I'm going to use A, B, and C in a different context. If I look at the equation, y equals ax squared plus bx plus c, and then I solve this for ax squared plus bx plus c equal to 0. What are the solutions to this? What's the quadratic formula say? The solution x is equal to minus b upon 2a plus minus b squared minus 4ac all upon 2a. Okay, remember that. What happens if b squared is less than minus 4ac and a and c are both positive? You get a negative number here. So when you solve a quadratic solution, you can either get real solutions, or if this is the square root of a negative number, what do we call the solution? You remember what the square root of minus 1 is. It's this thing called an imaginary number I. So if we solve this equation, and this, b squared, is less than 4ac. And if you remember, I don't know how many of you remember this. This was the trace of the matrix A, and this was the determinant of the matrix A when we set it up. I don't know who remembers that? Nobody. You guys got some studying to do. Okay. I'll give you a little hint, is that if you don't really master the stuff, it won't be that devastating in the final. What's more important is that you understand how to build the equations and do the phase plane analysis and everything else. But this is important if you really want to go on with mathematics and use it in any modeling, and you read papers and people are going to talk about these formulas and these sorts of things when they do analyses. This is called a complex conjugate pair of solutions. So it's got a real part and an imaginary part. So now it turns out that this is in some cases where you've got complex conjugate solutions, what happens is that you'll get e to the real part and an imaginary part. Does anybody remember this formula? E to the I theta is equal to cos theta plus I sine theta. Anybody, the Morse expression? Anybody remember that? So how many of you never looked at complex numbers? So do you remember once seeing that, but now it's like disappear from your head? When you have the exponential of an imaginary number, what comes in? Trigonometric functions. What if trigonometric functions do? They oscillate. So hence, if these solutions involve complex conjugate pairs of eigenvalues, trigonometric functions of time come in, which means you get oscillations. So when you get complex conjugate pairs, you get spirals. And if the real part of the complex conjugate pair is negative, those spirals are stable. And if the real part is positive, the spirals are unstable. Now, this stuff that I've said is like one step further than you can go in our textbook. And our textbooks are first course in calculus. There are textbooks that are first course in calculus that include this stuff. But our textbook doesn't include imaginary numbers. But all you need to know is that if you take a nonlinear system of equations, like the x1 dt is f1 of x1, x2, the x2 dt is f2 of x1 and x2, and if you linearize the system by calculating this Jacobian, what's called the Jacobian matrix. The Jacobian matrix is this matrix of partial derivatives. It's just called the Jacobian matrix. Okay. There. So here we've got this matrix of partial derivatives. This matrix of partial derivatives is 4 numbers. It's the 4 values that you get in the linearized system when you take the partial derivatives of f1 and f2 with respect to x1 and x2. And then you look at the eigenvalues of that. The eigenvalues of that matrix tell you whether your equilibrium is a node or a spiral or a saddle point. If your eigenvalues are both negative, it's a stable node. If they're both positive, it's an unstable node. If one is positive and one is negative, it's an unstable saddle point. If your eigenvalues are complex conjugate, then depending on whether the real part of the complex conjugate numbers, the real part being, when we do this, where is it? This is the real part. This is the imaginary part. When you solve for, in this case, x1 and x2, in our case, we're actually working in lambda because it's the eigenvalue, so I'll put lambda here. So you get the real part plus or minus the imaginary part. If the real part is positive, you get an unstable spiral. If the real part is negative, you get a stable spiral. Okay, that's enough to overwhelm you for today. I'll review this very quickly on Thursday. Again, all I'm interested in is you having the basic concept of you have a nonlinear system, add an equilibrium, you can linearize it and get the Jacobian matrix. You take the Jacobian matrix and look at its eigenvalues. And the eigenvalues tell you whether that equilibrium that you're considering, and the equilibrium you're considering is the one that when you take the derivative and evaluate it at equilibrium gives you your 4 numbers there. If that is, what is the nature of those eigenvalues? And that tells you everything. It tells you whether it's a saddle point, a spiral, or a node, and whether it's stable or unstable. And so you should know that it's only stable if either both eigenvalues are negative or the real parts of both eigenvalues are negative in the case where the eigenvalues are a complex conjugate pair. Okay, that stretched you to the limits of where we're going in this class. So I'll see you all on Thursday, and on Thursday we'll discuss the exam in more detail.